Good day, everyone. Today I'm going to go over the final module for the course, which is gases. So just a little bit of an overview before we get started. Number one is we're going to go over some of the parameters, i.e. state functions being pressure, temperature, volume. Then we'll get into the empirical gas laws, so both Boyle's law and Charles's law. Combined gas law, so in other words, combining the two into one and having it sort of be proportional between the three different state functions I just mentioned. Avogadro's law, which is actually to relate pressure to count of moles of a particular gas or count of particles, really essentially. Then ideal gas law and the gas constant. So this is going to be just for one particular gas, no mixtures or anything like that. Then, of course, since this is a chemistry course, we're going to incorporate stoichiometry and put the gas law, ideal gas law, into context. Gaseous mixtures, so partial pressures as well as mole fractions. Those will be particularly important for the next semester. Kinetic energy and speed of particles, so how fast things go relative to how big they are or how small they are. And then finally, getting into real gases, so accounting for volume as well as some intermolecular forces. Okay, so what's to be considered? Well, pressure mostly. So pressure is really going to be the gauge. So that's going to tell you, how much gas you actually have in a closed system. Okay, so really a measurement, again, of concentration. So concentration about sort of an aerosol mixture or aerosol component. So like that of a solution, right? So we think of moles per liter when we're talking about molarity. In this case, it's just pressure in a given fixed amount of volume. So pascals is the SI unit that you would, look up from, let's say, National Institutes of Standards and Technology and outside of the U.S., but for the purposes of this particular course, we're going to use atmospheres. That's not ATMs where you get your money. Okay, so other parameters like volume and temperature matter as well. Well, just how? Okay, well, we'll get into, if you were, let's say, to double the volume and you still had the same amount of gaseous particles that are bouncing off the walls and off each other elastically, if you're expanding that volume, that means the pressure would be reduced, right? So if you're not adding any more gas molecules into a particular system, then the pressure is going to drop. Okay, let's say if you're at a fixed volume and then you increase the temperature, that's going to create more kinetic energy and more energetic stimulus for those particles to bounce around at a faster rate. Okay, so we'll take a look at all of that. Now, some of the empirical gas laws that you see here, first being Boyle's law. So Boyle's law is simply the product of the pressure times the volume is going to be fixed. So P1 times V1 is equal to P2 times V2. Okay, so that means that pressure times the volume is going to be proportional. So it almost looks like a Chanel meets an alpha sign right there. So it's like this loop and then a C that's kind of fused onto it. This means proportional. Okay. All right, and this is going to be under isothermic conditions. So that means a static temperature. So if it's 25 degrees, it's going to stay at 25 degrees. Okay. Now on to Charles's law. So Charles's law is simply V over T being constant as well. Okay. So, or in other words, proportional. Now, this is to take place when things are isobaric, meaning, if you pay attention to the weather report, you see barometric pressure. It's going to be somewhere, in Memphis around 760 millimeters of mercury displaced. That's just the pressure of the atmosphere. So that's exactly at 1 atmosphere, 1.00 atmosphere. So that means that you would have a static pressure. In other words, an ambient pressure. Okay. So once you adjust any of these parameters, things all change, i.e. why they refer to them as a state function. So this is something you already knew. If you take a look back at, let's say, your phase diagrams and things like that, when you have a higher pressure, you tend to see that things are a little bit more condensed unless you really try to heat things up under high temperature. Okay. So think of it that way. So temperature, pressure, even delta H, those are all considered state functions. So naturally the two should combine since they share the parameters, right? So P1 times V1 over T1 is going to be equal to P2 times V2 over T2. So you can kind of think of it the same way in terms of the math for dilutions. So M1 times V1 is going to be equal to M2 times V2. What is the constant here? It's really the amounts, right? Because if you dissolve something into, let's say, a liquid medium, things aren't going to go out until all that water is evaporated off, for instance, in an aqueous solution. Now, same thing kind of goes here, unless you were to let some kind of pressure, or i.e. gas, escape, right? If this were in a closed system and you change any one of these parameters, it's going to be proportional, okay? So solving for a projected volume, take a look at problem 10.66 on page 472. Again, this isn't really chemistry. This is really more along the lines of thermodynamics, but it's a pretty simple question to get you started. So just to kind of align some of the metrics here, if you will. So P1, V1, and T1. So P1 is going to be 1.17 atmospheres. So slightly higher than normal atmospheric pressure at sea level. V1 is going to be equal to 200 liters. Okay, and then the temperature is going to be 293 K. Okay, so remember that if you're using one type of unit on one side, it should be equal to the same unit on the other. You don't want to go sort of cross-pollinating with different units because you're going to get different results. So with that said, P2 says 63 millimeters of mercury. So 63 millimeters of mercury, if we want to get everything into atmospheres, we're simply going to do the conversion of that. So 760 millimeters of mercury displaced. So if you've ever looked at an old school barometer, I'm sure you could look one up on the internet. It's kind of a U-shaped tube, right? So let's see here. So if you had a glass tube or something that's going to hold mercury inside of it, that Hg stands for mercury, by the way. Okay, so let's say it's like this, and let's say this is pressure applied. That mercury is going to shift over this way. So that means if there's, let's say, an atmosphere pressure reading that's higher than 1 atmosphere, and that's going to start to push or create more force to displace this mercury. So I'll just write Hg right here. Okay. Now, if you were to, let's say, apply a vacuum, right? So in other words, this would be V initial and then V final. So if you're going from a higher to lower, then, or displacement, if you will, then that means that, you know, you've increased pressure or you've reduced pressure. Okay, so again, vacuum is the opposite of applying pressure. So whenever somebody says negative pressure, quote unquote, that's kind of inaccurate. All right, so back to, so I was just trying to explain the units here. Back to atmospheres and converting, divide 63 millimeters of mercury displaced by 760 millimeters of mercury, and then, you know, that's going to be per atmosphere, so atmosphere is going to stick on the top. You'll be left with atmospheres. What you're looking to solve for is V2 for the question at the temperature of 210 Kelvin. Okay, so there's a drop of about 83 Kelvin there. Definitely a drop in terms of atmospheres. So we're going to need to figure out what V2 is going to be. And remember that if we plug this particular equation above and solve just for P2, we would divide we would divide both sides by V2 and multiply it by T2 to just solve for P2 and have everything on the other end. So P2 is going to be P1 times V1 times T2, again, multiplying both sides to cancel this out. Then you're going to have, let's see, T1 divided by V2 there on the bottom, right? Okay, so plugging everything in, 1.17 atmospheres for P1, 200 liters for V1, and then 210 Kelvin for T2. Okay, so Kelvin and atmosphere should cancel out, and you should just be left with liters right here. So 293 K, and then this conversion is 0.083. So substantially lower than the initial. Okay, so again, atmospheres cancels out, Kelvin cancels out. It would be really to your advantage if you canceled out all your units, so you're going to be left with one because there's going to be a lot of bookkeeping here. Okay, so that value, P2, is going to be 2.02 times 10 to the 3 liters, putting that into scientific notation. Okay, so it would actually be 2.0 since we're having two significant figures right here. So this would be 2.0 times 10 to the 3. Okay, so let's work into chemistry. What's been learned here? Avogadro's law states that equal volumes of any two gases at the same temperature / pressure contain the same number of molecules. Okay. So a constant is needed to relate pressure, volume, moles, and then temperature. So in comes the gas constant. Sorry, I crossed out R value. Got my wires crossed with TLC, sorry. My bad. Okay, so pay attention to these units, all right? So for two different types of applications here, the first is going to be for stoichiometry. So this is directly related to moles with liters and atmospheres divided by moles and Kelvin, right? But look at here for thermodynamics. So that's going to be a little bit different. Okay, so a couple orders of magnitude off as well. but notice how it says joules right here. So this is really more, again, geared towards thermodynamics, and this is geared towards stoichiometry. Now, the ideal gas law is going to be P times V is equal to N times R. Again, gas constant times T. So T should be in Kelvin, V should be in liters, P should be in terms of atmospheres, and N is just going to be, excuse me, the count of moles. Oof. All right. So let's take on a couple of problems here. Keep it short and sweet. Problem 10.74. Okay, so we need to figure out moles, or sorry, first we need to figure out moles of N2. So this is on page 472. Let me read this real quick for you. Okay, 10.74 says, liquid nitrogen-powered car. Students at the University of North Texas and the University of Washington built a car propelled by compressed nitrogen gas. What a bunch of smarties. Okay, the gas is obtained by boiling liquid nitrogen, which is certainly easy to do, stored in a 182-liter tank. What volume of N2 is released at 0.927 atmospheres of pressure and 25 degrees C from a tank full of liquid N2? The density of liquid N2 is going to be 0.808 grams per ml. So let's first figure out how many moles of N2 we need to solve for. So moles of N2, so little n of N2, meta N. Okay, so 182 liters is a volume that we're working with. Okay, so we have a density, so this is going to be your rho value. So it's going to be 0.808 grams per 1 ml. Okay, and then that conversion factor, 1,000 milliliters, is going to be equal to 1 liter. Okay, and then 1 mole of N2 is going to be equal to 28 grams of N2. Okay. So that conversion is going to be 5.25 times 10 to the 3 moles of N2. Okay, so that's going to be your N value, right? So now they're looking to calculate what volume is released. So the volume released is simply going to be N times R times T over P. So remember that PV is equal to nRT. We're just dividing everything by P. Okay, so it's just a simple matter of plug and chug now. So 5.25 times 10 to the 3 moles of N2. So then our R value, which is we're going to use for stoichiometry, which is 0.0821 liters times atmospheres over mole times Kelvin. And then plugging in 298 K is equal to 25 degrees C. Okay, so dividing all of that by the pressure, which is going to be 0.927 atmospheres. Atmospheres strike out, moles strike out, Kelvin strikes out, and then you're just left with liters. So that value is going to be 1.39 times 10 to the 5 liters of N2 gas. Okay, pretty straightforward. just a little bit of conversions here and there, right? So just pay attention to your units and make sure they stack up with your R value. Okay. Next problem, 10.76. A balloon vendor at a street fair is using a tank of helium to fill her balloons. The tank has an internal volume of 45 liters and a pressure of 195 atmospheres at 22 C. So that gauge of 195 atmospheres is the amount of helium she has in that tank. Okay. After a while, she notices that the valve has not been closed properly and the pressure has dropped to 115 atmospheres. Well, vendor, you got to close that seal. Anyway, how many moles of helium have been lost? Okay, so really what we're looking at here is delta N. Okay, so we know what delta P is just from the change in volume, or sorry, in pressure. We started out with 195 atmosphere. Remember that the volume is going to be fixed. So 195 atmospheres down to 115. Okay. So that's a difference of, and you want this to just be positive, right? You're not going to get a negative pressure. You're not going to get a negative 0 degrees or negative Kelvin, what have you. Okay, so that difference is going to be 80 atmospheres of helium that's dropped. Okay. And then don't forget, you also have your volume, which is going to be fixed at 45.0 liters. Temperature is 295 Kelvin. And then your R value is going to be constant at 0.0821 liters, atmospheres, moles, Kelvin. Okay, so with that said, we're looking to solve for the change in moles of helium displaced. Okay, so we don't need to know what the atomic mass of helium is. We're just looking to solve for the moles. So recall that PV times V is equal to N times R times T. So we're looking to solve for N. N is just going to be equal to P times V divided by RT. Okay, so that change in pressure is going to get plugged into where P is. So you're going to put 80 atmospheres times the volume, which is 45.0 liters. Liters, atmospheres, mole times Kelvin. Okay, and then 295 K. Okay, so plugging and chugging again. Atmospheres cancels out, liters cancels out, Kelvin cancels out. Moles is going to be inversed on the denominator, so it's just going to be regular on the numerator. So that's going to leave you with 1.5 times 10 to the 2 moles of helium lost. Okay, so let's apply this to stoichiometry now. So we just solved for moles up to this point. Moles or volume, given the amount of pressure, etc. Okay, so problem 10.89, page 473 on the next page. Rescue breathing devices. Self-contained rescue breathing devices like the one shown in figure 10.89 convert CO2 into O2 according to the following reaction. So that's going to be 4 equivalents of KO2 plus 2 equivalents of CO2 gas, and that converts to 2 equivalents of potassium carbonate, and then 3 equivalents of O2 gas. Okay. So the question says, how many grams of KO2, so mass of KO2, are needed, how many grams of KO2 are needed to produce 100 liters of O2 at 20 degrees C and 1 atmosphere? Okay, so that means our volume to be produced of O2 is going to be 100 liters. The temperature is going to be 293 K. Pressure is just going to be 1 atmosphere. Okay. So no one's going to go into hypoxia at 1 atmosphere. All right, so we need to figure out the mass, KO2. So in other words, if we can solve for our moles of O2, we can relate it back to this empirical chemical equation and then work back with KO2. So the molecular weight of KO2 is 71 grams per mole. Just sloppy behind the envelope calculation there. Okay, so moles of O2, so N of O2 is going to be equal to P times V over RT. So plugging in 1 atmosphere, volume 100 liters. Temperature 293 Kelvin. And then your R value, once again, is 0.0821 liters, atmospheres, moles, Kelvin. Atmospheres out, liters out, Kelvin out, moles. That calculated is 5.54 moles of, whoops, jumped ahead of myself, 4.16 moles of O2. My apologies. Okay, jumping the gun here. Now, to solve for moles of KO2, we're going to take 4.16 moles of O2. Relationship is 3 to 4. So 3 moles of O2 to 4 moles of KO2. Plug in the molecular weight. 1 mole KO2 to 71 grams of KO2. Okay, and that's going to leave you with 5.54, which I crossed out up above. Oh, and then times the, 71 grams. So 5.54 moles is what you're going to be left off of in terms of amounts, but Again, if you're multiplying by the molecular weight, you're going to get 3.94 times 10 to the 2 grams of KO2. Okay, so now we're going to get into gas mixtures because, as you know, not everything is going to be entirely pure. Gases can kind of whiz about one another and create a gaseous solution even. So if you want to think of a particular gaseous solution, you can just think of regular old air that's all around us. We're taking O2 in. So the majority of it is going to be N2, so it's going to be inert. A little bit of O2 there to keep us breathing, even at some higher altitudes. A little bit of argon there. Smaller, much smaller percentage of CO2, even though that's increasing. And of course, trace water, pollutants, what have you. Okay, so these are all gauged. Individual components are gauged by either partial pressures or mole fractions. So let's take a look at mole fractions first. Problem 10.98, and that mole fraction is really exactly what it sounds like. So the count of all the moles of components divided by a particular mole or molar amount of one component is going to give you the mole fraction. So it's really a decimal place. Or a percentage. Right. Timed it by 100%, whatever. Okay. So problem 10.98 on page 474. I'll read that out to you. Problem says a gas mixture contains 7 grams of N2, 2 grams of H2, and then 16 grams of CH4. What is the mole fraction of H2 in the mixture? Okay. So just converting 7 grams of N2 to moles is going to be, so remember there's going to be 14 grams to every amount of nitrogen per mole. So if there's 2 equivalents, that means that 7 is going to be divided by 28 to give you 0.25 moles of N2. Okay, 2 grams of H2. So that should be exactly 1 mole, 1.0 moles of H2. And then 16 grams, 16.0 grams of methane is going to yield exactly 1.00 moles of methane. So if you were to sum these 3 values up together, you would have total moles of gas. These are all gases. We're doing chapter 10, gases. All right, so total moles of gas is going to be 2.25 moles. Or 2.3, whatever you want to really shave it down to. Remember that you're going with the lowest decimal place, so it's going to be really 2.3 moles. Okay, so what is a mole fraction of H2? So 1 mole of H2 and 2.3 moles. 2.3 moles of gas. That is going to be 0.43 for that mole fraction. So that would just be expressed as X H2. Okay, this kind of funky looking X that you see right here. So XH2 plus XN2 plus XCH4, that's all going to be summed up to 1. Okay. So, 2.3 moles of total gas is going to be quote unquote 100%. All right, so a little bit different now, partial pressures. So pressure total pressure of a system is going to be equal to the pressure of component 1 plus the pressure of component 2 plus the pressure of component 3 plus yada, 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 depending on how many there are. So in other words, it's cumulative, just like the total moles of gas, right? So if everything kind of, or additive, everything kind of sums up together. Okay, so problem 10.11, or 110, sorry. A mixture of 0.056 moles of carbon is reacted with 0.117 moles of O2 excuse me, in a sealed 10-liter vessel at 500 K, producing a mixture of CO and CO2. The total pressure is 0.640 atmospheres. What is the partial pressure of carbon monoxide? All right. So we have moles of carbon, which is going to be 0.56. Moles of O2, which is going to be 0.117. Okay. Okay. Now, 2 equivalents of C plus an equivalent of O2 gas. Remember that C is going to be in the solid state. This is not a gas. So it's going to yield 2 equivalents of CO. And then 1 equivalent of carbon is going to combine with 1 equivalent of O2 gas to yield 1 equivalent of CO2. Okay, so we have our temperature, which is 500 K. We have our volume, which is 10 liters. Okay, we have P total, which is 0.640 atmospheres. Okay, so see how you would figure out the partial pressure of CO. So pause and take a couple minutes and see what kind of math you can come up with for this one. All right, so if you thought that you needed to combine the 2 equations into one, you're on the right track. First thing you want to do is figure out what the limiting reactant is between the carbon and the O2, since those are the 2 reactants that are going to produce CO2 as well as CO. Okay, so whatever is going to generate the least amount of CO2, because again, we're looking to solve for CO, is really going to be the limiting factor here. So remember that for every 1 CO2, you're really going to have to generate 2 equivalents of CO. Okay. So there's a 1 to 2 ratio between the 2. And this would make sense because if you have 0.052 moles of CO2 that you could form, let's say everything's ideal, right, going from left to right. you're going to have a little bit of excess of O2 remaining, right? Because, you know, this is hypothetically how much you could form with O2, but if you run out of carbon, then you're not going to form as much, right? So looking at the moles of O2 consumed, that's going to be 0.156 of the moles of C. Remember, that's a limiting reactant, converting it into the moles of O2, which is going to leave you with 0.104 moles of O2. Now, going back to the equation, remember this is going to be empirical, 2 equivalents of O2 to 2 equivalents of CO. So in other words, it's going to be the same amount of CO that's going to be formed. Okay, so 0.104 moles of CO. So moles of O2 remaining, this is an error. You started out with 0.117. Again, that's going to be an excess. And only 0.104 moles was used up. So that means 0.013 moles of O2 remains. Now, if you were to calculate the total or 100% of the moles of gas, you're going to take your moles of CO2, adding to moles of CO, and then adding moles of O2 to give you 0.169 moles of some solution of a gas. Okay. Now remember that P total is going to be equal to P1 to P2 to P3, but we have moles now. So in other words, we can estimate with mole fractions to kind of go back and calculate without having to calculate each one of these partial pressures. Okay, so if we have a mole fraction of CO, we have the total pressure of the system. Okay, so that's where the 0.640 atmospheres comes in. You multiply that by the mole fraction, and that should give you an estimated amount, which is going to be 0.394 atmospheres of carbon monoxide. Woof! A lot of work. Don't expect any questions like that. I'm just trying to get you guys to follow some of the, law of conservation of mass, et cetera, et cetera. Okay. All right, so molecular or gas particle kinetics are the last things I'm going to discuss here. So displacement. Remember that we're going in the X, Y, and C directions, so Z directions, not C directions. So there's going to be 3 axes, not 3 axes that you're going to chop wood with, right? So thus, it's the velocity, not the speed. So again, this is going to be bouncing all over the place along the X, Y, Z, axes under different vectors and what have you. So speed is relating to, going along, let's say, a flat, 1 or 2 dimensional direction. Okay, so how do gas particles move? Mostly through elastic collisions. So again, things don't kind of all cluster up and hang out together. Things are bouncing around in elastic form. So you can think of like a tennis ball just bouncing off the walls ad nauseum, right? So the effusion, that means that a particular particle is going through, let's say, a small hole, like of a solid or a polymer. For instance, if you were to say have a birthday party for someone on a Friday, you leave the balloons there, you all go get tanked or whatever you do. You come back on Monday, you see that the balloons are deflated. Well, whatever imperfections are in those balloons or voids, that's where that helium or whatever they use to fill up those balloons will escape. Okay. Now, diffusion's a little bit of a different story. So it's really gas particles cutting through other gas particles to kind of permeate and cover a whole space. So let's say somebody all the way across the room opens up a can of tuna. In a very short period of time, you're going to smell that tuna, right? It's just a matter of time before you smell what's in there. So, not initially, because again, that stinky permeating smell or whatever, or odor has not kind of filled up the whole atmosphere just yet. Okay, now temperature is influenced by heat energy. You recall Q, right? All right, so what are the base units of joules? Simply going to be kilograms times meters squared over seconds squared. Okay. So the blank of a gaseous particle may influence its velocity relative to heavier or lighter gas particles under the same conditions. That is going to be the molecular weight, right? So, or the mass of that particular particle. So the molecular weight or atomic weight, you're talking about an inert gas, or more specifically a noble gas. Okay, so heavier ones are going to move slower under the same ideal conditions versus lighter ones, right? So chromatography. So gas chromatography is just kind of sidestep here. Gas chromatography is used to measure different components in a gas mixture up to 400 Daltons or 400 grams per mole. Okay, so this is a very good type of technique to understand the purity of a drug or a solvent or whatever you're looking to analyze and kind of understand its concentration, or even, you know, a mixture of products or whatever. Now back to velocity. Okay, so this mu here is representative of velocity. So RMS just stands for root mean square. So here's the square root, a mean of all three directions. So that's where 3 comes in. So 3 times the gas constant, you would use the thermodynamic one this time. So joules per mole Kelvin is 8.31 times, or sorry, 8.31 joules per mole Kelvin. Times the temperature all over the molecular weight, and you would square that. Sorry, this is going to be equal to. Okay, so let's compare methane to propane. Take a look back at problem 10.29 on page 470. Okay, so we'll look at that of methane. We're going to look at that of propane. I'll just write that as PRO. Okay, so 3 is going to be there times the R value, which is going to be 8.314 times 10 to the 3 joules, or sorry, 8.314 joules. Remember, it's going to be kilograms per meter squared, second squared. We just want grams in this particular instance, right? Because remember, the molecular weight is going to be expressed in grams per mole. You got it. So in other words, 10 to the 3 grams per meter squared, second squared. Okay. So that meters per second is where everything is going to relate to your root mean square velocity. Sorry about that. Okay, so temperature is going to be equal to, sorry, this is also going to be moles per Kelvin, degree Kelvin. So T, this is going to be at 298. So under standard conditions, all this over the molecular weight of CH4, which is just going to be 16.0 grams per mole. Okay. We would do the same for propane, except there's going to be a different molecular weight. think I put one too many brackets in there, whatever. Okay, and this is all going to be over molecular weight is 44 grams per mole. Okay. So, we'll just work with three significant figures. Remember, this is going to be a constant. This is going to be a constant as well. But we're going to be left with meters per second because if you take the square root of something squared, it's just going to be left with whatever those units are. So moles strike out, grams strike out, Kelvin strike out. And then you're just going to be left with meters squared. So for CH4, that's going to be 682 meters per second. Then propane is what you see in those big cylinders outside of Walgreens. It's going to be 411 meters per second. Okay, so those are the two speeds. Now, what temp is propane have to be equal to the root mean square velocity of CH4 at 298. So that means root mean squared of propane when root mean squared velocity of CH4 at 298. Okay, so what we're going to look to do is we're going to equate the two together. This is going to be way easier than you might have expected because there's going to be a lot of repeats. Remember, it's going to be relative to the temperature as well as the molecular weight. Okay. So what all strikes out? Okay, so now if we're looking to solve for the temperature of propane where it's going to be equal to the speed of CH4 at 298, T of propane is going to be equal to molecular weight propane times temperature CH4 over the molecular weight CH4. Okay, so in other words, grams per mole on both sides are going to, or on both numerator and denominator are going to cancel out. Then you're just going to be left with temperature in terms of Kelvin. So plugging all that in, 44 grams per mole times 298 K over 16 grams per mole. Again, grams per mole cancels out and you're just left with Kelvin. So that temperature is going to be 820 Kelvin. Okay. I'll let you guys work on problem 10.33. We'll go over it for the review. Okay, so I've answered this already. Just rewind back if you need to. So the conceptual question, problem 10.33 on page 470. So I'll let you do that for homework. We'll go over during review. Okay, so to kind of wrap things up, things especially gases are not so ideal. Real gases and the van der Waals equation, so that's what you see right here in this big long-winded form, is to account for intermolecular interactions. So there's going to be a constant for each gas, A, and then volume represented as B. So these are both factors that change the overall pressure and volume quantities. Okay, so the amount of moles is going to be fixed, R is going to be fixed, T is going to be fixed. So we're going to compare what ideal pressure we can come up with versus real pressure. Okay, so with that said, PV, remember that for ideal PV equals nRT. This is problem 10.120 on page 475. So for the pressure, it's going to be equal to N times R times T over V. Okay. So plugging everything in, you're going to have 5 atmospheres. Or sorry, 5 moles times 0.0821 liters, atmospheres, moles, Kelvin, times 300 K, all over 1.00 liters. That's going to give you 123 atmospheres. So remember that number, and we'll compare it to what we're going to deal with the real pressure. So see what kind of sort of algebraic manipulation you can do to solve for P. So P is going to be equal to nRT over V minus NB. So in other words, you divide both sides by V minus NB. Okay. So P plus A times N over V squared is equal to nRT over V minus NB. So everything that I've done here is pretty much the same as what I did on the ideal pressure. But again, we're accounting for 2 different variables that are going to factor in here for a real gas, right? So if we're looking to just solve for P now, all we have to do is subtract both sides by this particular term. So nRT over V minus NB minus A times N over V squared. Be sure to have this in parentheses and that you square the whole thing. Okay, so everything you plug in, I'm going to make it crystal clear here. So 5 atmospheres, sorry, 5 moles times 0.082 liters, atmospheres, moles, Kelvin, times temperature, 300, sorry. Okay. All that's going to be over 1.00 liters minus 5.00 moles times 0.0427, and that would be moles over, or sorry, liters over moles. This is the constant, so B right here. Oops. Subtract all that by, is that 3.59? Yeah. 3.59 liters squared over moles, or liters cubed over moles squared. Ugh. Okay. And then 5.00 moles over 1 liter, all squared. Remember, you want to be left with, sorry, this should be liters squared atmospheres. Arg. So in other words, liters squared canceled out, moles squared, they cancel out because this is both squared. Okay, all of that is going to be equal to 66 atmospheres. So look at the difference of 66 atmospheres, taking into account the volume and intermolecular interactions, is almost doubled for the ideal. So is ideal very accurate? Not really. So this is really trying to give you more of an accuracy in terms of a real pressure or a real gas as opposed to ideally. Okay. I know that was a lot to take in. Rest assured that I'll kind of give you something to narrow in your focus for the final. And be sure to attend the review next week. All right, good luck on your third exam, and I'll see you later. Thanks.